Parametric equations give us a way of representing the x and y coordinates of a curve separately, making them based on some independent third variable, usually a t for time. We finish this chapter by looking at plane curves and parametric equations. Let's go. In section 10.7, we look at plane curves and parametric equations. So the idea behind this section is that there'll be some curve in the xy plane. That's going to be called a plane curve. And the way that we determine which points are on this curve are going to be given by a parameter. That parameter is usually t, usually stands for time. So it's more important in this section that we sort of see the motion behind the curve. One point leads to another point, leads to the other point, because they're all sort of in order, even if that order may not be the order that we normally think of. Let's go ahead and get some definitions here. Let x equal f of t. So that means that x is given by some function, and y is equal to g of t. And that means the y coordinates are going to be another function, where f and g are two functions whose common domain is some interval I, period, the collection of points defined by x comma y is equal to f of t comma g of t is a plane curve. The equations x equal f of t and y is equal to g of t, where t is in I, that's the interval where everything is defined, are called parametric equations of the curve. Finally, the variable t is called the parameter. Let's take a look at example number 1. Let x equal 3t squared and y equal 2t on the interval where t runs between -2 and 2. Complete the table of values, then graph the points and connect in order for increasing values of t. Display the orientation of the curve. So here we have the parametric equations that are going to determine the plane curve that we'll graph on the right. All we need to do is plug in t into the equation for x, plug in t into the equation for y, and then those form the two coordinates of the points, the x and the y. Then we'll graph them, we'll mark the t's, and then we'll discuss the orientation. So first, let t equal -2. X is equal to 3t squared. So -2 squared is 4. 4 times 3 is 12. 3 times -1 squared is 3. 3 times 0 squared is 0. 3 times 1 squared is 3. 3 times 2 squared is 12. Now let's look at the y's. Y is equal to 2t, so 2 times -2 is -4. 2 times -1 is -2. 2 times 0 is 0. 2 times 1 is 2, and 2 times 2 is 4. Now create these points. 12, comma, -4. 3, comma, -2. 0, comma, 0. 3, comma, 2. And 12, comma, 4. Let's graph each of these points. So we start with 12, -4. 3, -2. 0, 0. 3, +2. And 12, +4. Now this first point that we drew corresponded to t is equal to -2. And the graph went from t equals -2 up here to 3, -2. That's when t was equal to -1. Then it went from that point to the origin, and then around to these other points going that way. There are no arrows because we're on a finite interval for the t here. Let's go ahead and mark the other t values. T equals 0, t equals 1, and t equals 2. The way you mark orientation is by using a little arrow on the curve itself to indicate which way the values of t are increasing. Notice that on the bottom, even though the arrow is pointing to the left, that's still increasing. Increasing as far as on a parametric equation has to do more with the t values than it does with the x and the y values. So even though it's going to the left, which we normally associate with being negative, that's the increasing way that the t's are flowing. They flow from -2 to +2. And you can see here that this is a parabola. It has endpoints, but it's more or less a parabola. Example 2. Write the parametric equations x equals 3t squared and y equals 2t. T runs from -2 to 2 in rectangular form, and then identify the curve. Well, I already gave that away. We know it's a parabola. Let's see what the rectangular form would be. Let me start with y equals 2t. And because this has t to the first power, it's easy to work with. Solve this for t, and you get t is equal to y over 2. Let's substitute this into the x equation. So substitute. So x is equal to 3t squared, which would be 3 times y over 2 squared, which would be 3 over 2 squared is 4 times y squared. So we have x is equal to 3/4 y squared. And if I solve that for y squared, we get 4/3 x. And there it is. You recognize that from our section on conics. That is a parabola. Example number 3. Let x equal a times the cosine of t and y equal a times the sine of t on the interval where t is any real number. A is a constant that is greater than 0. Graph the curve and indicate its orientation. So we'll just sort of make up our own little table here. We have t, x, y, and the point x comma y. Since we're using trig functions, I think it'd be best if we used the standard radian angles that go around the circle. So 0, pi over 2, pi, 3 pi over 2, and then 2 pi. And then we just plug these in. X is equal to a times the cosine of t. So for t equals 0, a times the cosine of 0 is a, because cosine of 0 is 1. Next, a cosine of pi over 2 is 0. A times the cosine of pi is negative a. 3 pi over 2 gives us a times the cosine of 3 pi over 2, that's 0. And a cosine of 2 pi, we're back to the beginning, and that's an a again. Let's repeat that for the y's. A times the sine of 0 is 0. A times the sine of pi over 2 is a. A times the sine of pi is 0. A times the sine of 3 pi over 2 is negative a. And then a times the sine of 2 pi, back to 0 again. So these points are a comma 0, 0 comma a, negative a comma 0, 0 comma negative a, and then a comma 0. If I were to graph this in the plane, we would start at a comma 0, and we know that a is positive, so it does go out to the right. Then we would go to 0 comma a, then to negative a comma 0, and then to 0 comma negative a. If I connect these in order, using what I know about sine and cosine, it does in fact form a circle centered at the origin. With a radius equal to a. The orientation goes counterclockwise around the circle. So in essence, the t is really representing the angle. That works out really well this time. But be warned, it doesn't have to quite work out that way every time, where the t is the actual angle. It still represents a parameter, and there are things that you can do to make the parameter go clockwise instead of counterclockwise like this one. And you can stretch it and do all sorts of stuff. So this one works out really well. Let's go ahead and convert this into rectangular so that you can see what that looks like. So when dealing with sine and cosine, one thing that you can try is to square both the x and the y and add them together and see what happens here. So I'm going to start with x squared plus y squared. And that would be, making the substitution, a times the cosine of t squared plus a times the sine of t squared that gives me a squared cosine squared of t plus a squared sine squared of t. Then the question is, what can I factor from both of these? And the answer is a squared. That leaves me with cosine squared t plus sine squared t. But we know that sine squared t plus cosine squared t is just 1, so this ends up being just a squared. So the equation is x squared plus y squared is equal to a squared, which is a circle centered at the origin of radius A. Example number 4. Find the parametric equations for the ellipse x squared over 4 plus y squared equals 1, where the motion around the ellipse starts at the point 0, 1, moves clockwise, and requires 4 seconds for one complete revolution. All right, let me draw us a little picture here. We know that the semi-major axis is 2, and this is all centered at the origin. The minor axis, semi-minor axis, is 1. So it's going to go up 1 and over 1. So here's what the ellipse looks like. More or less. Now the question is, where is the parameter and how does it define the motion? Well, it's going to start at 0, 1. So it's going to start right here. I'm going to say that that is time equals 0, t equals 0. It's going to move clockwise, so it's going to move this way around the ellipse. And it requires 4 seconds to make one complete revolution. So in addition to the point 0, 1 being time equals 0, I'm going to say that that is also time equals 4. Now the other thing I can do is I can say, well, there are really 4 distinct points that I want to hit during one revolution. I'm going to start at time equals 0. Then, going clockwise, I'm going to make that time equals 1. Then, here at the bottom, time equals 2. Then over here, time equals 3. And then moving back around to the top would be time equals 4. So that works out great. 4 is a perfect number to use with this. Now the question is, I have to figure out how to create the parametric equations for this. So let's go ahead and break down the table of values that we need to use in this problem. So for time goes from 1, 2, 3, 0, 1, 2, 3, and 4. We know what the x values are going to be. Since it starts at the top, the x is 0. It moves around clockwise to where x is 2, then back to 0, then to -2, and then to 0. Similarly, the y's, where time is equal to 0, that starts at its top there, so that's going to be 1. Then it rolls clockwise to where y is 0, then -1, then 0, then back to 1. So basically, I need to come up with an equation whose graph would fit these values, the t and the x, and then the t and the y. So let's start with the x. So I need to find some function f that uses t as the variable, and it takes on these values right here as the result. Well, since we're dealing with an ellipse and we're sort of going around, that tells me I need to use sine or cosine. Let me see what graph actually gets produced here. Now remember, t is the input and x is the output. So it's not quite your traditional x and y, it's t and x. So we have 0, 0, and then we have 1, 2, then we have 2, 0, then we have 3, -2, and then we have 4, 0. And look at that sinusoid right there. Beautiful. And then the question is, what graph is that? Well, first, we know it's going to be sine because it starts at the median, it starts at the origin here. So it's some sort of sine function. We know the amplitude. It goes up to 2 and down to -2. So it's going to be 2 sine of something t. The question is, what is that t? Remember, what is that number in front of the t? Well, remember that it affects the period. the period here, capital T, is equal to 4, and that should be 2 pi over the omega. So solving for omega gives me 2 pi over 4, which is pi over 2. So the parametric equation that does this is 2 times the sine of pi over 2 t. Now we need to do the same thing with y. So y is going to be equal to some g of t function. Let's make a little graph. We know that this one is going to be a ty graph, like so. And the points are 0, 1, 1, 0, 2, negative 1, 3, 0, and 4, 1. Like so. And the question is, which graph is that? Well, that's our old friend, the cosine graph. And notice that this one has the same period, so it's still going to be pi over 2 times t. The amplitude is 1, so we don't have to write anything in front of the cosine. It's a 1. What is our parameter sort of bounds? Well, we just need to go from 0 to 4, and that'll work out fine. Now, how can we be certain that this is the correct parameterization? Parameterization is the word that we use when we parameterize an equation by finding the parametric equations that suit the curve. Well, we can check it. So let's check it. We're going to start with x squared over 4 plus y squared. If it checks out, I should be able to substitute in my parameters and end up with what this was originally equal to, which is a 1. So let's do that. So the x squared over 4, I'm going to write that as 1/4. Then I'm going to substitute in the x parameter, which is 2 times sine of pi over 2 times t squared, plus substitute in the y parameter, which was cosine of pi over 2 t squared. And now we just work this out. So it's going to be 1/4 times 2 squared is 4. Then sine squared of pi over 2t plus cosine squared of pi over 2t. The 1/4 and the 4 cancel. And that leaves me with sine squared of pi over 2t plus cosine squared pi over 2t. But we have sine squared plus cosine squared, and they are the same angle. And so that's equal to 1, and that checks out. Example number 5. For the rectangular equation y equals 7x squared minus 9, find two different pairs of parametric equations. So parameterizing a plane curve is not unique. You can shift the parameter t that you use. You can use different formulations for the x and y. All sorts of things can happen. Now, there is a very quick way to parameterize y equals 7x squared minus 9. That would be to just let the x be equal to the t. And so that means y is equal to 7t squared minus 9. That is not very exciting, but it is a parameterization. Is there some other way that we could parameterize this? And the answer is yes. we could let x be equal to t divided by the square root of 7, and then y is equal to t squared minus 9. So essentially what I'm trying to do is build up this piece, the 7x squared, from the x and then interfacing it with the t. Now let's see how that actually works out. To check this, I would solve the x equation for t, which would be t is equal to the square root of 7 times x. And then I would plug that in to the y equation. Y is equal to t squared minus 9, so that's going to be the square root of 7 times x squared minus 9. But the square root of 7 squared is 7, and then x squared minus 9. So that works out as well. Now what's interesting is, again, the equation y equals 7x squared minus 9 is a fixed set of points. But using parameterization number 1 versus using parameterization number 2, you would use different t values to produce those points on the curve. So a t value when t is equal to 0 may not be the same as a t value in the other curve. But that gives you some flexibility whenever you need certain things to happen. For, like in the previous ellipse question, we needed the motion to start at 0, 1, so we just used t equals 0 to do that, and then everything else fell into place.